This video explores quantum colors, showing how subatomic physics paints the foods we eat. Specific frequencies of reflected light create the visible colors we perceive. Subatomic energy transitions are what dictate light absorption. In the classical world, objects exist in one valid state at a time. For example, an elephant is either gray or multicolored. However, in the quantum realm, a particle can exist in a superposition of multiple states at once, meaning it can be gray and multicolored. Quantum particles are delocalized, meaning they lack a single specified position. While a classical particle has an exact position, a quantum particle's location is described by a probability function, indicating it is somewhere around a certain region with high probability. Nature loves symmetries, and matter behaves exactly like light. Both the photon and the electron possess a dual character, acting as both a wave and a corpuscle. The electron forms a standing wave around the nucleus. When confined, waves can only exist in perfect harmonics. Because the boundaries are fixed, only specific wavelengths can fit perfectly, creating discrete harmonics like the first, second, third, and fourth harmonics shown here. In three-dimensional space, confined electron waves create complex geometric clouds known as orbitals. These shapes, such as s orbitals, spherical, and p orbitals, dumbbell, are not physical paths but represent where an electron is most likely to be found. Confining the wave into a potential well shows that the width of the box dictates which wavelengths can fit inside. Higher energy levels pack more waves into the exact same space. Because only certain waves fit, energy levels are strictly discrete. Electrons jump between precise energy levels, and each specific jump corresponds to a distinct wavelength, which, in turn, corresponds to a distinct color of light. Conjugated molecules act as physical quantum boxes. The electrons within these systems are delocalized, meaning they are free to move back and forth, trapped only by the length of the molecular chain. The equation of reality for these quantum boxes is that size dictates color. The length of the molecular box L determines the energy gap E, which then dictates the frequency or color of light absorbed. A longer molecule means a smaller energy gap. In the case of a carrot, $beta $carotene contains delocalized electrons in a relatively long box. The energy jump from the highest occupied state to the lowest unoccupied state perfectly matches the energy of blue light. By absorbing blue light, the remaining light appears bright orange. The cranberry juice effect demonstrates shape-shifting quantum boxes. Changing the acidity, or pH, physically alters the structure of the pigment molecule, and a structural change means a change in our quantum box's length, L. Shrinking the box shifts the color spectrum. The conjugation length at high acidity is greater than at low acidity. When L shrinks, the energy gap changes, and the absorption peak drops, shifting the juice from a deep, bright red to a washed-out pale red. Color is a biological imperative, not just an accident of physics. Colorful fruits and vegetables are packed with polyphenols, molecules that have perfectly evolved to utilize this exact quantum effect. They are visually appealing and vital to consume. Grape-skin polyphenols, acting as an, quote, edible sunscreen, are the ultimate quantum shield. Their molecular box length is tuned to absorb high-energy, damaging UV radiation, protecting you from the inside out.